Breaking space news, the most powerful telescope in space.
We took a picture of an exoplanet outside our solar system.
You've seen the headline, a planet with over a 99% chance of life. But here's the real question. What chemical pattern could possibly justify a claim that bold without slipping into hype? In the next minutes, we'll trace the decades-long hunt for a clean biosignature and why most maybe life signals collapse under scrutiny. Stay with me as we map the problem, the false positives that fooled us before, and the precise combination of atmospheric molecules JWST would need to see to push probability that high, plus how astronomers rule out the non-biological lookalikes. So what's the single obstacle that keeps every life-found headline from sticking? A clean, unambiguous biosignature, something in a planet's air that, by the rules of physics and chemistry, shouldn't be there without living processes keeping it topped up. Here's the core challenge. Astronomers don't stare at alien oceans or forests, they read light. When a planet passes in front of its star, a thin ring of atmosphere filters starlight and carves tiny notches, absorption lines, into the spectrum. Those notches overlap, smear, and shift with temperature and clouds. Planets aren't uniform either. Gravity, composition, and weather change how molecules show up. And chemistry loves tricks. A biosignature means a signal that requires biology to maintain, not just a molecule life happens to like. A habitability marker, on the other hand, points to conditions life could use, like liquid water, but doesn't imply anyone's home. That's where confusion starts. Oxygen sounds like life, but you can make it without cells. Methane feels biological, yet volcanoes and rock-water reactions produce it. Water vapor is common across the cosmos. It tells you a planet isn't bone dry, not that microbes breathe there. Each hopeful molecule has a non-biological look-alike pathway that can mimic the appearance of life. Even on Earth, the story isn't simple. During the Great Oxidation Event, oxygen in our air rose dramatically. But sunlight can split water vapor, letting hydrogen escape and leaving oxygen behind. On a dry world, or one with a strong ultraviolet bath, you can build up O2 without a single chloroplast. So oxygen alone doesn't close the case. This is why researchers lean on a deeper idea, disequilibrium. If certain gases coexist, even though they should react away under known conditions, something must be replenishing them. On our planet, life constantly pumps and consumes gases, holding the atmosphere far from chemical balance. The trick is to find combinations and ratios that, given the planet's temperature, pressure, and light from its star, don't persist unless there's an active source that looks very much like metabolism. Another headache sits upstream of the chemistry, statistics. Most worlds we can study with today's instruments are puffy mini-Neptunes with thick envelopes that hide a rocky surface. Small, Earth-sized planets with thin, clear skies are harder targets and often cloudy or hazy, which mutes their spectral fingerprints. Fewer suitable planets mean wider error bars and more room for false positives. Enter how JWST actually reads those tiny dips. The telescope spreads the light into wavelengths and collects a time series as the planet moves across the star. Then, spectral retrieval comes in. That's a modeling approach that tests millions of atmospheric scenarios, adjusting temperature profiles, cloud heights, and gas abundances to find which combinations reproduce the observed pattern. It's Bayesian, so it doesn't just fit. It weighs how plausible different explanations are, given the data and prior knowledge about physics and chemistry. The key, then, isn't a single molecule. It's a set of gases seen together in ratios that would self-destruct without constant, directed replenishment. Think of it like finding logs and ice cubes in the same campfire. Something must be actively replacing what the flames should consume. If the modeled atmosphere can't sustain those pairings under any lifeless process, the odds tilt. So the roadblock has never been detection alone. It's the non-uniqueness of chemical signals. Oxygen, methane, water, and others can come from lifeless geologies and photochemistry. Confidence rises when multiple molecules line up in a pattern that resists every non-biological explanation, anchored by the planet's climate and the star's radiation. Next, let's stress test the famous false alarms under this tougher rulebook and see what, if anything, makes the new pattern different enough to count. If Mars, Venus, and a handful of exoplanets have thrown us off before. What would it take for one planet's spectrum to actually cross that 99% line without crumbling under a second look? Start with the old traps. The Viking landers on Mars ran metabolism tests that gave mixed signals, so scientists dug into the soil chemistry and found reactions that mimicked lifelike behavior without cells. Mars later coughed up methane bursts that looked intriguing, then faded or shifted with the seasons, pointing to geologic or photochemical quirks rather than microbes. Venus had its moment with acclaimed phosphine detection, but when teams reprocessed the data and inspected the instruments, calibration and line shape assumptions took center stage. Each time, the life reading fell back into the noise, or into chemistry you can do with rocks, light, and time. That is the pattern to avoid. A single line can be an artifact, a warm pixel, a calibration mismatch, or a signal that a different molecule shares. A lone molecule can have a lifeless origin. Mineral surfaces can catalyze reactions that look metabolic. Ultraviolet light can generate or shred gases in ways that impersonate biology. When those alternatives remain on the table, confidence cannot pass the threshold. So the modern playbook works like a forensic audit. You list energy sources, sunlight, internal heat, lightning. You count geologic fluxes, volcanic outgassing, hydrothermal vents, rock-water reactions. You calculate photolysis rates for key molecules under the star's ultraviolet output. You include atmospheric escape and surface sinks. Then you ask, with those inputs and the measured temperature-pressure structure, which combinations of gases survive, and for how long, without biology adding or removing them. The goal is to box in every abiotic route until only contrived, low-probability corners remain. Now the kind of pattern that stands out looks like a cocktail in disequilibrium sustained over time. One classic candidate is methane and carbon dioxide together with depressed carbon monoxide. Another is oxygen or ozone coexisting with abundant methane while hydrogen cyanide stays low. These aren't just names, they are relationships. Methane and oxygen chew through each other quickly, so keeping both around means something must constantly feed them. Ozone tracks oxygen and stellar UV, so its level pins down the photochemistry. Hydrogen cyanide spikes when high-energy chemistry runs hot. If it's muted while methane stays high, that constrains lightning, flares, and other abiotic drivers. Low carbon monoxide deserves special attention. Lifeless carbon chemistry often leaks CO as a byproduct, whether from high-temperature outgassing or photochemical cracking. On Earth, microbes and surface reactions mop up CO, pushing it down. So seeing robust methane alongside carbon dioxide, but with unusually little CO hints at active consumption rather than passive production. Those gas ratios don't live in a vacuum. You fold in the planet's gravity and size, which set how the atmosphere stratifies and how fast light gases escape. You anchor the temperature-pressure profile with the spectrum's continuum and the star's color, which defines UV flux. A cool, quiet star can preserve methane longer. A hot, active star burns it off. If the measured levels defy the photochemical lifetimes expected under that specific UV environment, geology alone has to work miracles to keep up. This is where statistics keep you honest. Retrieval models let you pit lifeless baselines, volcanic outgassing, serpentinization, pure photochemistry, against biosphere-like fluxes that add methane or oxygen and remove CO. You score each hypothesis by how well it reproduces the full spectrum across multiple wavelengths, and by how simple the required inputs are. When null models demand extreme, fine-tuned parameters to survive, and biosphere models fit cleanly without contortions, the odds slide toward life. So a 99% case looks like this: a repeatable, multi-gas disequilibrium pattern captured across several transits, stable over months, with carbon monoxide and other abiotic byproducts suppressed, methane and carbon dioxide or oxygen-ozone balanced in ways that outpace lifeless chemistry, and all of it consistent with the star's ultraviolet output and the planet's climate constraints. To try to break it, astronomers would schedule more transits and different instruments, chase phase curves to catch day-night chemistry, and compare with high-resolution ground spectra that can separate blended lines and confirm the same ratios. If the pattern holds while the tests get harsher, the claim hardens, and the next observation window becomes the most valuable time slot on the calendar. Confidence doesn't come from spotting a single line in a spectrum. It comes from showing that every lifeless recipe, volcanic outgassing, photochemistry, mineral catalysis, fails to produce the same multi-gas pattern under the planet's actual light and climate. That's how a probability climbs, not by hype, but by elimination. So, does the disequilibrium combo we outlined pass your threshold?
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery,